and they fluoresce at a specific wavelength that a camera with a lens on it will be able to capture. So that isolates those chemical species. So what happens is you get images like the ones on the right, and using edge detection, an edge is indicated as a regional difference, or indicates a regional difference in the image. So a sudden change in brightness is what an edge is. So from these images, you can see that the edge is actually pretty obvious. Like you can just look at it and tell where the edge is. The problem is that the cameras were taking images at 10,000 frames per second. So there are hundreds of these images. So it's less tedious to just use an edge detection algorithm to go through the images much quicker. So an edge detection algorithm can be used to simplify an image for the processing or determining an object's location or shape, as I said earlier, such as the flame. And this is an especially important aspect when you don't know what the object's shape is or where it's supposed to be. So it's also important for isolating useful information from the noise. So in the case of flame edge detection, PLIF images of formaldehyde and hydroxide were taken, and in order to determine where the flame edge was, we overlaid the images, and wherever the edge contours overlapped was where the flame edge was. So a good edge detection should be able to detect the max number of edges in an image while keeping all of the edges in the same location at the same orientation. So it also needs to be able to distinguish between noise in an image and an edge and do all of this at a reasonable speed. So some common algorithms include Canny, Sobel, and Pruitt. And Canny is one of the most common, and it's also very accurate, but it's computationally expensive. And Sobel and Pruitt are good for images with well-defined edges, but respectively, they may detect false edges or miss weaker edges. But the above algorithms may struggle with the noisy images that we may encounter when trying to take images of a flame. So this is just showing all of the previous algorithms mentioned in use for two different images. And what you notice is that the top image with the peppers is a lot more complex, and it also has a lot finer edges. So Canny does a better job at detecting edges for this image than Sobel and Pruitt, but you notice at the bottom that the simpler image, Sobel and Pruitt are kind of similar to the way Canny performs. And given that Canny is computationally expensive, you would want to choose those over Canny. So in the case of a noisy image, you'd want to choose fuzzy logic. And that's because fuzzy logic is particularly good at dealing with noise in images. So these images are just comparing a noisy fuzzy logic edge detection with the Canny edge detection. And the paper that I got this image from, they had actually developed their own fuzzy logic algorithm. And so this is what makes a fuzzy logic algorithm desirable, is the fact that you can tune the fuzzy logic algorithm based on the requirements of the image or what you want to figure out. The only downside would be that it's kind of slow compared to the others. So a fuzzy logic algorithm is characterized by its fuzzy inference system. And this is the part of the fuzzy, the membership plane is the part of the fuzzy logic algorithm that you can modify. So first you would input an image, which ideally you would input the gradients of the image. And then it enters the membership plane through a process known as fuzzification. And it goes through an input membership function, an output membership function, and then it's defuzzified to help us visualize the image, because once it enters the membership plane, it doesn't make sense. So the fuzzification process is basically when the image first enters the membership plane, and the input function converts the values of the pixels into some membership values between 0 and 1, while also applying minimal thresholding. And this goes into an output function, which can then be used for even further thresholding. So after the output function, when it goes to, when you defuzzify the image, what you're doing is you're applying logical statements to that output function's image in order to determine what those values mean. So if you could say that any value between 0.5 and 0.7 was a certain pixel color, and that would translate it for you. But these are some common membership functions that are used for fuzzy logic. But in this case, we used the triangle and Gaussian functions. So our input function was the Gaussian function, and we varied the standard deviation in order to control the width of this curve. And our output function was the triangular function, which we varied the vortices of the triangles in order to determine what the intensity of the edge would be and how strict we wanted our edge detection to be. So now I'm just going to go through the basic process of implementing fuzzy logic edge detection in MATLAB on a general flame image. So first, we had filtered the image, and the reason why we did this is because there is actually a lot of edges within this image by itself. So filtering the image, since we want only the outer contours, it kind of helps blur the inside of the flame so that the outer contours are the most obvious edges. And then we solved for the gradients. So these images you can't really see very well, but there's kind of an outline of the gradients of the flame in both the X and the Y direction. And then we plug those gradients into our fuzzy inference system. So what's happening is, say you have a gradient of 0, that means that there isn't an edge there. So when it first goes into the Gaussian function, it outputs a membership value of 1. And then that membership value of 1 is inputted into the triangular function. And because it's underneath the curve that designates a white pixel, that's basically how we use our rules to say, hey, this is a white pixel. So we say if the gradient of an image is in the X direction is 0 and the gradient in the Y direction is also 0, then that pixel should be white in the output image. And if the gradient of either of the two in either of the two directions is some number other than 0, then I out, or the image, is black, or the pixel is black. So what you end up with is just the profile of the edge detected chemical species profile. And what you notice is that there are actually some edges that we don't need still inside, but this can easily be, like, with enough time, you could figure out the correct threshold values that works for you. So this was also done with formaldehyde in the same way, and this kind of just summarizes the whole process. And then you take the two images from the same time step, and you find their contours using the fuzzy edge detection algorithm, and then you overlay the contour of one of the images onto the PLIF image of the other image. And what you end up getting is, in this method of overlaying images, is that any yellow pixel is the flame edge. So just to summarize, edge detection is useful for determining flame shape and location. And in the case of a noisy image, such as the flame images we had here, fuzzy logic is good to use because you can modify membership function, parameters, and threshold values, and then which helps us determine the characteristics of the flame by allowing us to find some way to figure out where the edge of the flame is. So in the previous image of the overlay, the first yellow pixel from the bottom would be your liftoff height. And so that would help us, in turn, determine the quality of combustion. Yeah.
How would you realize if the edge is cyclically you add?
I'm not really sure.
Okay.
But I think like when you filter the image, you'd have to have some idea of what your accepted error would be for like where the edge would move. Yeah, you'd have to monitor that. Yes. Mm-hmm. Yes. Oh, so like filter after you detect the edge? I haven't tried that, but I'm sure that could work to some extent because some of your edges, like the close edges here, maybe if they're too small, if they're small enough, then yeah, maybe it'll get through. But if you try to edge detect it again, what might happen is if the ones that are like have like a larger width, it might start encroaching on the outer contour as well. So.
Have you looked at, let's say you filter this,
Mm-hmm.
then you apply the edge detection filter image.
Oh, yes, I have. You get all kinds of, yeah, on the inside, yeah.
but then going back to like filter then threshold.
Mm-hmm.
Threshold first, without filter, is what you get. Look like just qualitatively when you look at it. Work with. So then I have all these edges, but I want to now remove the ones I don't element. Perhaps at different gradient levels, lower gradient thresholds than you care about. For those things that have been looked at.
No, they haven't.
Can I actually build off your question? I think I have an answer to it though, because often the noise in these images shows up as a bright pixel, not just as a slightly bright pixel, but as a full bright pixel.
Okay.
So if you were to simply thresholding wouldn't eliminate that noise, right? The noise is above that threshold level. If you apply like a Gaussian filtering, then you could lower the intensity of the pixel to the noise pixel below the threshold floor. But that is an interesting point about it does work for certain types of noise.
Okay, so people do that then, depending on the circumstance. Mm-hmm. And I guess another question too about this image here: are these line of sight images?
No.
Or are these like?
It's from the side.
It's line of sight. Is this the shadow?
What does the line of sight mean?
Well, so we took a laser sheet.
Yeah.
And barring with the laser, you could just image just what's inside that sheet.
Oh no.
This
is
photograph where it's shining through the full body. Got something back with
it. Yeah. This is like the laser sheet was like this thin rectangular portion.
Okay.
And
so this is being illuminated with a laser.
Yes.
Okay, so that's not line of sight.
So yeah, so it's from the top, and then yeah.
Okay. Any other questions?
Did you have that slide where you overlaid the high and low edge?
Okay.
Showed the yellow pixels?
Yes.
So yellow was where the red edge and the green edge were both present? Yes. Okay.
And this image isn't synced properly. This is from some old data. So we had to kind of manually like pull the image together till it looked like properly. But in the actual thing, the images were synced. So you would better be able to see where the yellow pixels were, and it would be more accurate. Okay.